it didn't make the noise that I think we're going. Okay, so this is what you guys had last night to do. And so we're going to like rotate back to implicit differentiation. I hope you guys remember implicit differentiation. We'll see. I'll review it with you as you go. So looking at the graph, let me get one, Mr. You'll just pass all those papers out. Looking at the graph, where does this, it's not a function, it's a relation. Where does this relation have vertical tangents? What ordered pairs does it have vertical tangents?
-2 and 0 and 2 and 0.
What about horizontal?
No.
There's no horizontal tangents. Good. Okay. All right, in which quadrants is this curve increasing and then decreasing? So what do you guys think about increasing?
1 and 1.
Yep. Decreasing is going to be 2 and 4. All right, so here we go. Let's see if you guys remembered implicit differentiation. So I'll just remind you, in case you forgot, you still do the derivative like normal, but if your variable is y, then you're going to need to do what?
dy over dx.
dy over dx. Very good. Okay, so we have x squared over 4, so we're going to multiply by the 2 and take 1 away. All right, and then negative y squared, multiply by the 2 and take 1 away, but it was y, so we're going to do a dy over dx. All right, and then the derivative of 1 is just, what's the derivative of 1?
0.
0. Okay. All right, so that's how you start it. You finish it by solving for dy over dx. So this one isn't too complicated. We're just going to move the x over. And then divide by negative 2y. And there's multiple ways you can write this. I just went ahead and did x over 4y. If you did 1/4 times xy, that's perfect too. How'd it do? Did you get it? Sweet. Okay, and then number 4 says, how does dy over dx support your answers for questions 1 and 2? So I'm guessing that's where you might have stalled out when you were doing this. It's okay, we'll talk about it. So let's first talk about, I want you to write this down because we are going to do a lot of examples, but we're not going to do another example that involves vertical and horizontal tangent lines. So you might want to write this here so you can use it later because you definitely have a problem you have to do with that. And we don't have a ton of space. But if we're talking about the derivative, and the original graph has a vertical tangent, what do you know about the derivative? It should be what? Undefined. So horizontal tangent, the derivative should be 0 because the slope of a horizontal line is 0, but the slope of a vertical line is going to be undefined. So vertical tangents occur when dy over dx is undefined. So if we're looking at our dy over dx, what would make that undefined? 0 where? 0 in the denominator when y is 0. So just in general, if we're trying to find where a derivative is undefined, we want to know when the denominator equals 0. Okay, so what we'll do is we'll take our denominator and set it equal to 0, which is kind of obvious that y is going to be 0. Now sometimes, like the question I made up for your homework, I asked just like what is the y value where there is a vertical tangent or something like that. This one we want to show that is these actual ordered pairs. So now that we know what the y is, how do we know, or how do we find what the x is that goes with it? We go to the original. Very good. So what we'll do, and I know there's not much space, but I'm going to go back up here. I'm going to make this y 0, so we get x squared over 4 equals 1. And then we'll just solve that by multiplying by 4 and taking the positive and negative square root. So that's why you have those ordered pairs of 2, 0, and negative 2, 0 for your vertical tangents. Alright, so real quick, I'm going to fill in what we do for horizontal tangents. Even though this didn't have one, I'll show you why. Alright, and we just said a second ago, the horizontal tangents happen when, let me zoom in a little bit, when the derivative is 0, and that's going to be the numerator. Alright, so our numerator is x. So we do get an x value that you would think maybe there would be a horizontal tangent there, but whenever we plug it back into the original, we get negative y squared equals 1. Or y squared equals negative 1. Is that going to happen? Not with real numbers, so that's why there are not any horizontal tangents. Okay, and then we also have to talk about the other answer for number 2, which is where this relation was increasing and decreasing. So I'm going to move up here. Alright, so if our derivative is x over 4y, and we want to get increasing, we want that derivative to be positive. And so if we're looking at quadrants and just looking at x and y's, how can you divide that and get a positive? What divides to give you a positive?
Positive and positive, or negative and negative.
Exactly. So if we want dy, in this case, this rational dy over dx is going to be positive when x and y have the same sign. So in this case, that was in quadrant 1 and 3, and then we want negative for decreasing. So it's going to be x and y have different signs. And then for 5, when is the curve concave down and when is the curve concave up? So what do you guys think about down?
Quadrant 2.
Mm-hmm. So that's down?
Quadrant 1.
And that's down, good. And then up is going to be 1 and, wait, hold on. This is going to be 3 and 4. I just wrote it wrong on paper. Alright, and then they found the second derivative for us, which was kind of nice. And then how can we use this equation to support your noticings about the concavity of the curve? So this is the second derivative. If we want concave down, what do we want for the second derivative?
Negative.
Yeah. Okay, so the only variable that is in our second derivative is y. And so we want to be able to cube a y and divide it by a negative and get a negative for concave down. So that's going to happen when y is positive. Alright, and then which is going to be in quadrants 3 and 4. Okay, so I wanted you guys to do that yesterday to kind of get a head start or get you thinking about the lesson that we're going to do today. Because implicit differentiation, we just don't use it that much for it to be super solid in your head. But it needs to be because it comes up over and over again. So implicit differentiation can be used to find the first and second derivative of relations, or any kind of curve that cannot easily be solved for y. And so that's the main thing you have to remember. If it can easily be solved for y, just solve it for y and use regular differentiation. But sometimes, like all the ones we're going to do today, are not easily solved for y. And so we have been talking a lot about critical numbers. Well, whenever it's implicit differentiation, we call it critical points. And sometimes I might say points when it's supposed to be numbers, but the reason is because they're critical points because the x and y values, they are the x and y values where the derivative is either 0 or undefined. All right, and what is a critical number of potential? Potential relative maximum. Very good. So we are going to talk about that today, relative extrema. Okay, and then we're also going to talk about when a curve is increasing and decreasing. So do we use the first or second derivative to make that decision? First derivative. So dy over dx is positive. We'll have increasing greater than 0. And decreasing dy over dx is less than 0. And then what do we use for concavity? Second derivative. So concave up, we want that second derivative positive. Concave down, we want that second derivative negative. So it's the same things we've been doing. It's just slightly more difficult because we have to use implicit differentiation. We have to think about x's and y's more than we had before. Bless you. All right, so on number 1, we are going to consider this curve. So we have the curve, we have the first derivative, and we have the second derivative. So this is nice. We don't have to do all the derivative finding. We just have to use it to answer the question. So A asks us to find the critical points of this curve, and we're going to justify our answer. So the critical points are when that derivative is either equal to 0 or undefined. So anytime we want to find when the derivative is equal to 0, we need to set the numerator equal to 0. Alright, so that's going to give us the x part of a critical number, or critical point, 0. So let's go ahead and find the y that goes with that by plugging 0 into the original. Oops. Alright, and so you can kind of see that pretty quickly things go south. So we get that y squared is equal to negative 5. And if we're talking about real numbers, which we are only talking about real numbers, that's not possible. So what do you guys think that means about x equals 0? It's not a critical number. So there's no point on that graph when x is 0. So we just did a little extra work that isn't useful, but that's okay. All right, the other situation is whenever that derivative is undefined. And the derivative will be undefined when the denominator equals 0. All right, and then I'll go back in my original equation and make y 0. All right, when we solve it by taking positive and negative square root, we get a value for x when y is 0. So that means we have 2 critical points. 1, 0 and negative 1, 0. So B is kind of a question like you had on the what about us worksheet, where we want to know what's happening just in a quadrant. And so what I do when it's a quadrant question is we want to know if the curve is increasing or decreasing in quadrant 1. So that's going to be the first derivative. Whoops. dy over dx. So I'm going to plug in just the signs of numbers in quadrant 4, not an actual order pair. So in quadrant 4, is the x positive or negative? Positive. So I'm going to just put in a positive for x values. What about the y? Negative. So I'm going to put in a negative for y values. So when I go to that first derivative, I'm going to put a positive in for x. Right, so if I put 5 times a positive, I'm going to get a positive. I'm going to put a negative in for y. I'm going to get a negative down there. So when I divide a positive by a negative, it's going to be a negative. Alright, so what do you guys think? We're going to be decreasing. And then it tells you to justify your answer. We're going to have to use some definitions. When we justify in calculus, we always have to use calculus. So that means we have to talk about derivatives. Alright, so I would say something like since dy over dx is less than 0 in quadrant 4, and then you can say the curve, or you could go back and use the actual, if you have the actual equation for the curve, you can use that. Oops, we're not talking about concave now. It's decreasing. There. No, I don't like you guys to say the curve or the function or whatever. Sometimes though, you don't have a choice. Like it doesn't give you an equation for it. It's not called something like f of x or whatever. But in this case, we have the equation, so I went ahead and used it. Okay, and then we're going to do something similar on C. The difference is instead of using the first derivative, what are we going to use? The second derivative. So we're going to take our second derivative, and we're going to put in a positive for x and a negative for y. Now on your second derivative, it only uses y, and so that numerator is just automatically going to be negative because it's always negative 25. And then we're going to put in a negative y, and we're going to cube it. So if you cube a negative, what do you get? Negative. So that second derivative is going to be positive, which means we're talking about concave up in that quadrant. And then on the next example, we have this kind of crazy function. It's not a function, it's a relation, this crazy relation that is not easily solved for y. So we're going to go ahead and make sure, as we do this problem, we're going to use implicit differentiation. And the first question is about increasing. Now I've been really specific lately that a function can't be increasing at a point. So I actually reworded this so it wouldn't confuse you. So I reworded it to increasing or decreasing on an interval containing a certain point. So we can't actually plug the point into the derivative, it'll make it. A little easier to do than just putting in a positive and negative. Okay, so you guys ready? So to decide, make this decision, what do we need? Derivative, which is the answer every day. All right, so you guys, let's find this derivative. The left side is pretty easy. The right side, we're gonna have to do the chain rule and worry about the variable being y. So see if you guys can do that on your own, and then check with me in a second. Alright, and then this isn't the final answer, but we're going to we do the derivative of natural log of something. That something goes on the denominator. The numerator is the derivative of that something. And then because the variable is y, we have to do a dy over dx. Now before I finish this, I would probably go ahead and reduce 8y over 4y squared. It'll just make it easier in the long run for us to finish this out. Alright, and then we're going to multiply by the reciprocal of that to get dy over dx. So it looks like it should be 9x squared y over 2. Y'all okay with that?
Why do you multiply by the reciprocal?
To solve it for dy over dx.
When you're doing the chain rule, where does the natural log go?
Well, when you do the derivative of the natural log of x, it's just 1 over x.
Okay.
But whenever it's not x, it's 1 over that thing, but then you multiply by the derivative of the 4y squared. Does that make sense?
Kind of. Yeah. I'm just wondering. It's fine.
The natural log isn't part of the derivative.
Oh, it's not part of the chain rule? Or yet? Oh.
Okay. Alright, so here we go. We have our derivative, and we want to know what's happening in an interval that contains this point. So I'm going to take that point, and I'm going to plug it in for x and y. Now normally, I would just say, oh, you just need to know if this is positive or negative, but we actually need this to do the next question. So I'm going to finish it off and find the actual value is 9/2. And because this didn't say justify, it just wants you to answer the question, increasing or decreasing. I'm just going to answer that question. What do you guys think? Increasing. So positive is going to be increasing. Oh, that's wrong. There we go. 9/4. Okay, and then part B, we are going to determine if the relation is concave up or down at the point -1/2. So to do that, we need the second derivative. All right, and I am going to come up here. I'm going to rewrite this derivative a little bit easier for us to find the second derivative. So I'm just going to make it 9/2 x squared times y. Same thing, just easier way to find the derivative. All right, we are going to have to do implicit differentiation. What other rule are we going to have to use to find this derivative? Product rule and power rule. Product rule is what I was looking for though. So when I do a product, I am going to have 9/2 x squared be one of the factors and y be the other factor. Alright, so when I do the product rule, I'm going to leave that 9/2 x squared alone, and I'm going to multiply by the derivative of y. dy over dx. Good. Then I'm going to leave y alone, and I'm going to multiply by the derivative of 9/2 x squared. Should be 9x. Good job. Now we could make this simpler, but I don't think we need to because we're just going to plug a number in. I would leave it like that in this case. And then just go ahead and plug in our values. So it's going to be 9/2. And then I'll square negative 1. And what about that dy over dx? Do we know what that is? All we have to do is plug in the 9/4. It's because we've already plugged in negative 1 and 1/2. So we can just plug in that 9/4. Alright, and then it's 9 times negative 1 times 1/2. Now we really just need to know if this is positive or negative. So I'm going to do enough to make that decision. That's going to be 81/8 minus 9/2, or 81/8 minus 36/8. What do you think?
It's positive.
Definitely positive, concave up. Whew. These problems are taking a long time. But you guys are remembering a lot of things, and I love that very much.
I was trying to do the product rules in the chain rule for some reason.
Oh, I see. It looks like a product.
No, I was just having a moment.
If you guys are doing these at home, or even if you're in here and you want to know what that graph looks like, there is a Desmos graphing calculator that actually is kind of awesome for relations. And you guys, I think, are probably going to take the ACT one more time, right? Are you guys going to? Well, there's a Desmos calculator on the ACT, and I've given it if it's on the computer. Now, if you do it on paper, you're on your own. You got the yellow calculator. If you do it on the computer, there's one that's a pull down. I've given it on the computer many times on Saturday. I've never seen one actually pull down the graphing calculator. They just always leave it scientific, and I want to help them, but I can't. But this graph, you can just go to Desmos and you can type it in. And I don't think there's any way that the yellow, like the TI-80 whatever calculators can do a graph like this, but here it is. Now I honestly don't know what those two dots are. Oh, they disappeared. Okay, there you go. They're not really there. So here we go. We said increasing in that point. So negative 1/2 is right here, and that interval is increasing, and it is also concave up. So it's kind of a crazy looking graph. So one of the things that unfortunately for you guys you haven't learned about is like ellipses and hyperbolas. I helped Sadie with it one day, and the parabolas that open horizontally. So if you're taking the ACT on a computer, you can just type it in and see what it looks like. All right, sorry. Last question. So this one, we have this equation. We have a differential equation. We have the derivative equation. And we know 1 point on the function, or on the equation. And we're going to determine if it's a relative minimum, relative maximum, or neither. So for it to be a relative minimum or relative maximum, what has to happen at the derivative? 0. Good job. 0 or undefined. Oh, I love it when you guys remember stuff. All right. So I'm going to take that derivative and I'm going to plug in this point. Now we're not going to let the fact that it has sign in it confuse us because we know the unit circle very well. So we're going to put 1 in for y and we're going to put 2 pi in for x. What is the sign of 2 pi?
0.
Yeah. And so that is going to be 0. So it is a critical point. So that means that it is a potential relative maximum. So now we have to decide what it's going to be. Now this is not a good one to do the first derivative test because you would have to test points on each side. Well, we could know angles on each side, but we wouldn't really know the y's that go with those angles. So we're going to have to do the second derivative test. So let's find the second derivative. And we are going to have to do the product rule. One factor of your product is y, and the other is sine of x. All right, see if you guys can do this on your own. about y needing the dy over dx. So on the product rule, you're going to leave y alone. So leave y, but then you multiply by the derivative of sine. So y, you don't need dy dx, so it'll just be y. And then what's the derivative of sine? And it's not plus this time. So it's going to be y times cosine. Okay, and then it's plus. Leave sine alone and multiply by the derivative of y.
We have to answer it here. There's need.
Alright, so that should be your second derivative. Y'all good? Oh, alright.
Yeah, I got it. Oh, wait. No.
Yeah.
You might have done it in the
Did it
wrong order.
backwards.
Some of y'all got it. So you leave y alone, multiply by the derivative of sine of x, then leave sine of x alone and multiply by the derivative of y. Alright, and then again, when we did this before, we tried to make this prettier, but today we're plugging in numbers and we don't care if it's pretty.
I thought the derivative of sine was negative cosine.
Derivative of cosine is negative sine though.
Oh, okay.
That's alright. Alright, so we're going to plug 1 in for y, and we're going to plug 2 pi in for x. And in the place of dy over dx at 2 pi 1 is going to be 0. Alright, what about the cosine of 2 pi?
0. 1.
Alright, and now this sine of 2 pi is 0, but we don't need that because it's multiplied by 0, so we end up with 1. One is obviously a positive number. So let's take a second about the second derivative test. So we have a critical point, and at that critical point, the sign is positive.
Is it concave?
Minimum. So it's concave up, which means we're going to have a minimum. But it does tell us to justify our answer, so we're going to have to do all the things. Alright, so the reason it is going to be a relative minimum is since dy over dx equals 0 and d2y over dx2 is greater than 0 at 2 pi 1. Now they want you, if this was a free response question, they want you to mention the second derivative test. I don't know for sure if you get the point with or without it, but definitely you'll get it with it. So by the second derivative test, and this is where we have to say the curve. We can't, it's not called anything, so we're going to say the curve has a relative minimum at 2 pi 1. Okay. What questions do you guys have? Alright, don't forget when you're doing your assignment and you get to one and you're like, oh, I don't remember her doing one like that with the vertical and horizontal tangents, so look back at the paper that has pink on it. So that's where you can find that.